Hello, everybody. So this will be another video as well, which will begin to deal with the propositional equivalences, which pertains to the tautologies, contradictions, and equivalences. Although that we were able to discuss this a part of their propositional logic a little earlier, however, this is actually the step-by-step that you will begin to really deal with when it comes to um, with working with this particular details. Okay, no worries because we'll begin to work on this step by step. I'll be in order for you to really understand it well. Okay, no worries in that. We will begin to do it really well. Okay, now let's actually go ahead and um deal with it here. So propositional logic, as what we've mentioned, it is a branch of logic that deals with a proposition which are declarative statement that can either be true or false. It's important lies in helping to form logical reasoning by analyzing the structures of arguments and the relationship between statements. So we were able to discuss that earlier that we're trying to work on with true or false statements. And then those are the statements that either be true or false. They will be simple and complex. So here then pertains to propositional proposition is a basic unit in logic. Is a simple statement that has definite truth value, either true or false. For example, this case, blue is a proposition is can derive as either true or false. As what I mentioned, that this is just as referring to the statement if this is being quantified to be as true or false. Now, the importance of this one, in terms of logic and problem solving, as this is the fundamental and simplifying logical expressions, improving logical relationship between different statements, and the equivalence. These equivalences help in logical reasoning, mathematical proofs, and computational algorithms. So our goal here then is we'll begin to check if they are related to the other propositions, rules or laws as well. We'll begin to check that in the later part. Now, logical connectives are symbols used to connect a symbol to form more complex ones such as and so on and so forth. Each connective has a specific truth value that defines how operates on its input. So as what we have stated earlier, that will be from the propositional logic, we will begin to use the logical connective in order for us um, to combine specific statements as well. Now, propositional equivalences refer to logical relationship between propositions that are always true or always false. These equivalences are essential for simplifying logical expressions, making it easier to evaluate their truth values and outcomes during reasoning. Meaning to say class here, then we are trying to calculate if either the first statement is true and the second statement is false also, and we're trying to work on if they are equivalent to different rules because we will need to calculate that basically. Why equivalence is important in logic? This is to simplify complex logical expression, making it easier to reason about their truth or falsity. They are essential for tasks such as simplifying logical formulas, proving theorems, and optimizing computations and algorithm and digital circuit. This is really important, class, as we can definitely verify if this is equal o kung if in accounting may arata balancing, but here then this is also a way of balancing them if they are related to each other in terms of specific particular um rules. So, or laws. When two expressions are logically equivalent, if the first rules here and the second rules here, if they are equal to each other, so therefore they are equivalent to each other. Are logical equivalent when after every possible combinations of truth values or for the middle components, the truth values of the two expressions are identical. It is determined by constructing and comparing their truth table. So, as what I have stated, class, say for example, um, we have here the formula as T and F for times and F times T if they are equivalent, for example. So T times F, that is actually that's gonna be false, diba? False times T will be gonna be false. So they are equivalent because they do have the same value. That's how we will begin to work on the equivalence, meaning they are having the same value. Tautology, let's deal with tautology. A tautology is a professional formula that is always true no matter the truth values of the individual components. It is a statement that holds true in all possible solution situations like P or not P, which is always true regardless of the value of P. Say for example, class, um, we have true, then or not true. Now, if you're going to simplify true or not true can be simplified as false, diba? So true, this is or, which is plus. So true plus false, that is true. So therefore, this is correct. Then, the same thing for false. False or not false. Okay, that is the same. Always true in nature. So always are logically valid because they are true every possible case, serving as logical truths that they play a crucial role in logical reasoning by providing universally accepted statements. Meaning to say, in tautology, whatever may happen, it will always equates to itself then. A true statement then. So example, P or not equals to P. I'm not equal, not P is a classic tautology where either P is true or P is not true, making the entire expression always true. This mirrors the real world example. It's either raining or not raining. So that is still definitely will become true because it will be if it's raining or not raining, it's, of course, that is redundant in nature. If we're beginning to work on that, so it will equates to true statement. It will still be not raining, diba? So, what will gonna happen? Okay, this is P. That is, let me just edit it for a while. In a while. For a while. So, let me just edit that. Okay. That is P. Now for P here, class, we have true or false. Not P, that is false. False will be true. Okay? So for P, because tautology is plus, di ba? So P plus F, so that will become true. F plus T will become true. That is correct. That's how tautology always work or will always become true. Now let's actually work on with contradiction. For contradiction, naman, it is a provisional formula that always false, no matter the truth values of its components. An example, it is the formula P and, that is and, not P. So which is always false because P and P cannot both be true at the same time. Meaning, say for example, here and is definitely calculating multiplication. Sorry, excuse for a while. I just sneeze. Now, here then, for true, what will gonna happen, class? We'll multiply that with not true. What will gonna happen? If this is not true, it will become false, diba? True times false, it is false. The same with false, not false. So not false is equals to true. False times true is equals to false. So that is actually contradiction, as always. So always false in nature are logical invalid as they never hold true and not under any truth assignment. They are used in proof to demonstrate the fallacy in certain assumption by showing that they lead to an impossible situation. So they are actually unsolvable cases. So example of, excuse me, P and not P is always false because it asserts that P is both true and false simultaneously, which is impossible. This reflects the real world contradiction. It is both raining and not raining. So of course, it will impact. It is impossible that it will rain, then it will not rain, diba? So that is unbelievable. Now, for example, here then we have the P, which is P and F. So what will gonna happen? P negation on not P. So the negation of P will become F. The negation of F will become true. So times true times false equals false. False times true will become false. That's how it works then. Hopefully that's clear. Now, we also have here what is a contingency. Contingency is actually a or operation that can be either true or false depending on the truth values. Its component, for example, P or Q is a contention because it is true when either P or Q is true but false when both are false. So that is just a disjunction. Situation dependent truth value. A contingency truth value changes based on the truth values of its individual components. For instance, P and Q is true only when both P and Q are true. And P or Q is true when either P or Q is true. So what is happening if P and Q is true? Only when both P and Q are true. Diba? So P and Q is true kung both P and Q are true. Of course, class, mag-true gid sad and kung duwa ang true. But sa P or Q naman, it is for contingency, this is definitely either true or either or and gali. I stand corrected. Now for P or Q, it is true in either P or Q is true. So at least one, di ba? So kung sa times yet true and true, mag-true siya. But for plus naman, at least one. True, true, plus true, tapos true, false, and false, true. Diba? That's how it works. Now, for example here then, P and Q or P or Q. P and Q is a contingency because it depends on both P and Q are being true. P or Q is another example which is true if either P or Q is true. So that is just negation and disjunction. And conjunction and disjunction actually, and or. So here then, we have the truth table for contingencies. The and are, this is the and this is the or. So this is the multiplication, this is the addition. So true and true will become true. True plus true will become true. True times false will become false. True plus false will become true. False times true will become false. False plus true will become true. False plus false will become false, and false times false will become false, and false plus false will become false. That's how it works. Now, the equivalence laws. For equivalence laws, class, damo ginidi are the foundational rules that allow us to transform logical expression into equivalent forms. They help in simplifying complex logical expression, which is crucial for logical proof and reasoning. So we actually do have many cases here. So what is the equivalence? So say for example, kung here sa TF, it must be equal to FT. Say for example, if multiplication ta, diba? So T times F equals false, and F times T equals false. So they are equivalent to each other. So we have categories of equivalence laws, types of equivalence laws. We have 12. So identity, domination, idempotent, double negation, commutative, associative, distributive, De Morgan's, absorption, negation, implication, and contrapositive. Let's try to work on that one by one. So the laws are used to demonstrate that are used to demonstrate that true statement are logically equivalent either by creating truth table where all rows match or by using this algebraic rules to transform one statement into the other. So we'll begin to check that later if the other statement here, class, the other side is equals to the other side. For example, this statement here and the other statement here, if they are equal to each other, they are equivalent. Now, for the identity laws, this is the statement. We have two laws that we do have under identity law. For identity law, for or and ni siya, how a statement combined with a false or true value behaves. So these laws simplify expression by recognizing the inherent truth or falsity of a certain logical operation. Meaning to say, if P will be going to work on with or false, it will become the identical of P. So for example, if P, we will begin to plus that with false, not P, diba? Not P, that is false. So not P, that is false. This is false. So P plus false or not P, of course, P plus not P, that is actually still P. So identical to itself. Now, for P and true, so say for example, P not true times to itself. True, this is true, and this is true. That is still true, or that is still P. So they are identical. So meaning to say, for P or false, if considering true and not true, that is false, true plus false, it will become true. That is identical. Hopefully you were able to understand that. It's really so simple. Even grade 1 can understand. that. My goodness. When you combine a statement, P with false, using logical or operation, the result will always be P, since the only way or can be true is P is true. Example, P or false becomes P. So if P is true, the whole expression is true. And if P is false, the whole expression is false. That is really simple. So for example, here sa truth table, we have the truth table here, P. The P is true and we have false. If true statement, the true statement of true is false, I'm sorry, sala ni Diho. Let me just, very good gini nga, nag-review. We're able to discuss this one by one because we can definitely analyze where we're able to have any kind of um wrongs, or for example. So let me just work on that. So sorry. So there, this one here will become true, right? So why? Because the false of the statement false will be true. So therefore, this is or is plus. So true plus false, it will become true, and false plus true will become no. We're trying to work on with false mangali. So that's why we should not edit that one. That is true gali. Ay, nako po. Don't be misled by myself. Since ang category tadi, sa false gidya, hindi siya statement nga, we're not quantifying that into ano gali. Kung true siya, i-convert na to into negation. No, we're not negating that one. We are adding that into the false statement. False gid siya, false accordingly. So kung mag-add kaya sa any statement that you will be going to add into the false statement, it will always be true. The P. It always be the P. Tapos kung mag-add ka naman sa false nga P, tapos into false, it will always be the P, which is the false. So F plus P plus F will always be P. F plus F will always be F. So therefore, that's how it works. So for example here, it is raining or it is false, like that. So it will become it is raining. So that's how it works. Hopefully that's you were able to listen that well, because sometimes I may not able to explain the first place really well, but I corrected that in the latter part. Make sure to really listen carefully, because we are not really perfect, and put into realizations that I can definitely memorize everything due to the 5 subjects that I'm handling. So, but it's okay to not be okay. Now, we also have here the AND operation or multiplication. So if you will multiply any P to the true statement, it will always be resulting to P. So when you combine a statement P with a true using the logical and operation, the result will always be P, since the only way AND can be true if both operands are true. So meaning P or and true becomes P. If Pi is true, the whole expression is true. If P is false, the whole expression is false. So what will gonna happen? So we have here the P is T and the P is F. So when you multiply that with true, true times true, it will become true. False times true, it will become false. So that's actually how it worked then. So that's gonna be the case here. So for example, it is sunny and it is true. So therefore, the result will be it is sunny. Now, for the domination loss, so we are calculating here a little bit. So for P domination, for domination naman, P or true equals true. So P and false equals false. So the domination laws demonstrate how combining a statement with true or false affects the outcome. These laws are essential for simplifying logical expression. So if we're trying to dominate here, hindi siya mag-result into identity. It will become returns to true to returns to false. Like for example, if you combine any statement with P with true using the OR operation, the result will always be true because OR only needs one true operand to be true. Example, P or true is always true regardless of P truth values. So say for example here then, P or true equals true. So say for example we have P, true and the false. So if we will multiply that with true statement, true and true, true plus true will always be true. False plus true will always be true. So here then naman, sa AND operation, if you combine any statement with P with false using the AND operation, the result will always be false because AND requires both operands to be true. So P times the false is always false no matter if P is true or false. So say for example here then, we have P true and false multiplied by false, it will always be false, okay? I will go to the store and it is false. Of course, it is false then. Now, we'll proceed with idempotent law. For idempotent law, this is P or P equals to P. P or P and P equals to P. The idempotent law show how combining a statement with itself doesn't change its truth value. These laws help to simplify logical expression by removing unnecessary repetition. For example, true plus true will always be true. Tapos, ang P naman, true. So, true and true, they are equivalent. So, they are equivalent to each other. Tapos, P and P. P and P. P times T. This is our, this is our P, the T. So, T times T equals true. Tapos, ang aton P naman, the other side is true. They are equivalent. Yes, they are equivalent because they do have the same thing. Okay? Now, that's how it works, man. So, P or Q, if a statement P is combined with itself using OR, the result is simply P because repeating the same statement does not add any information. Example, P or P is equivalent to P, meaning if P is true, the whole expression is true, and if P is false, the whole expression is false. Let's try to work on that. So, we have here the T and F. So, P or F. So, we are adding. So, T, we have the P, F, T, and F. So, P or P, we're adding T plus T. It will become T. F plus F, it will become F. That is correct. So, they are equivalent. This is another set, another set. So, combine, check if they're equivalent. So, equivalent pa si true into true? Yes, of course. False. Equivalent pa siya sa false? Yes, of course. Therefore, this is idempotent law. Now, for this one, P and P. This is actually for AND or multiplication. If a statement P is combined with itself using AND, the result is simply P because both operands are the same. And AND only requires both to be true for the results to be true. If P and P is equivalent to P, meaning if P is true, the whole expression is true, and P is false, the whole expression is false. So let's get to work on that. So say for example, you have the P, T, and F. So you're using multiplication. True times true, it will become true. False times false, it will become false. Let's try to check if they are equivalent to prove. True and true, is it equivalent? Yes. False and false, is it equivalent? Yes, that's equivalent. So therefore, this is in the idempotent law. So I will go to the store, it is sunny and it is sunny. Of course, it is sunny. That's how it works then. Okay, let's actually work on with another one. Okay, so let's actually move on to the double negation law. So for double negation law, this is definitely basic because states that two negations cancel each other out, restoring the original truth value of the statement. This law is used for simplifying simplifying expression involving negation. So in this one here, then, the double negation, we do have this one. If this is actually the not P, and not of the not P, so say for example, not of the not P. So kung not it is will equates to the P. Say for example, if true is our P. Now what is the not P of that? Not P is not true. So it will become false. Now we will get the double P, the double not P. So the double not P will become from the F, it will become true. So we'll see if that is equal to the true to the P. The P is true, so true and true is they are equivalent. So that is really good. Now, for this one here, for for this situation, when a statement is negated twice, it returns to its original form. The first negation flips the truth value, and the second negation flips it back. Example: if P is true, double negation is also true. If P is false, double negation is also false. We'll begin to see that one. So here, so P is true and false. So if the not P of the negation of P is false, so the double negation of P is definitely true. So if P is false, the first negation is true, the double negation will become false. So let's try to see if this double negation law, if they are equivalent. So true is equivalent, is it equivalent to the double negation? Yes, they are equivalent. False, is it equivalent to the double negation? False, I mean, that is correct. So that is really so simple. Now, here then, let's proceed with the commutative law. Commutative law is definitely basic. So we have here for or and for and. So the commutative law shows that the order of operands in both or and operation does not affect the result. This law specific logical expression by allowing you to rearrange terms. So I'll begin to calculate that later so that we can work on with that. For this one, we'll work on with or operation. Or operation is commutative, meaning the order in which you combine P and Q doesn't matter. Say, for example, you will calculate that first here. It must equal with this one also. Let's try to prove that later. So, P or Q is equivalent to Q over or P. If P is true, the whole expression is true regardless of Q's value. Let's try to see. So, if we have true and false as our set, we'll begin to check the combination. Combination is true, 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 false, true, and false, false. So for the combination of true and true, what will be the P or what will be the calculation for P or Q? True plus true is true. True plus false is true. False plus true is true. False plus false is true. No, that's not true. That is not true. For false plus false is false. Let me change that one because I don't want that to be misleading for everybody. Now, let me just go ahead and correct that. It will become true. Okay. Ups. Diin ko nag-save. Hindi na ang here. Okay. Because this is or, diba? So for false plus false, it will become false. False, diba? That's correct. Now, for Q over P, so let's try to or P. True plus true will become true. False plus true will become true. True plus false will become true. False plus false will become false. Why? Because in our or operation, because it's what we have mentioned, the or operation is either at least true statement will turns to true. So let's try to check if this is commutative or law. So for commutative or law, regardless of what will be the set that we'll begin to calculate first, P or Q or Q or P, if they are equivalent to each other. Is it equivalent? True and true? Yes. True and true? Equivalent? True and true? Yes, equivalent. And false equivalent. So this is commutative. Now, For this one, commutative in terms of and, meaning multiplication. The and operation is commutative, meaning the order in which you combine P and Q doesn't matter. So P and Q is equivalent to Q and P. If both P and Q are true, the whole expression is true. Let's try to calculate that one. So our and operation is what we have mentioned, that it will returns to true if the statement is definitely the same as true. So say for example, for P and Q, we do have this combination. So true times true, let's calculate this first, the P or and Q. True plus true will become true. True plus times false equals false. False times true is false. False, false, false is false. Now, Q and P. That is true and true, yes, true. False and true, that is false. True and false, that is false. False and false, that is false. So let's try to check if they are commutative. So P or on Q and Q or on P. True and true, yes. False and false, yes. False and false, yes. False and false, yes. So they are commutative, of course. That's good. Now, for associative law, it is different class. For associative, you will be going to apply the mathematics. You will calculate this first before you can calculate the whole. This is 3 set. And for this one here, you will calculate this set first before you will calculate everything. So the associative law shows that the grouping of operands doesn't affect the results of either or and operations. These laws allow you to rearrange terms with parentheses. So here then we can check the equivalence if calculating this one and this one will be equal regardless of the calculation. Let's try to work on with under or operation if it is associative, meaning you can group operands in any way and still get the same results. If P is true, the whole expression is true regardless of how you group the terms. Let's try to check that in calculations in a while. So say for example here, then I will go to the store, I will go to the park, I will go to the gym, I will go to the store, or the park or the gym. I will go to the store or the park or the gym. That are still the same. Now, for when it comes to truth table. So for this one, calculating that one is definitely as what we have mentioned. We have PQ and R set. So let's try to prove this first. So under before proving this one, we have to calculate the P or Q. P or Q I was not able to step by step the process here then, but of course we just have to put that here. P or Q will be here then. Okay. Now P or Q, let's try to move on, check that. True plus true, true plus true is true. Tapos true and false is true. Tapos false and true is true. Then false and false is false. Now, we're done with the P or Q here, and let's add that into the R, this one. True and true, that is true. True and false, that is true. True and false, that is true. False and true, that is true. This is actually the answer now. Let's try to calculate this right now and calculating this first. So we can put that here, the value of Q and R. Q and R, true plus true is true. Then false plus no. Q, false plus false is false. Tapos true plus false is true. False plus true is true. Now what can we work on this? We're done with this one. And let's calculate P plus QDR. This one. So T plus true is true. Tapos true plus false is true. False plus false plus true is true. Then false plus true is true. So actually, apat na kabilog ato na calculate here then, but of course, in this one, actually, we can form many combination because this is 3 sets. But of course, this is just an example, and make sure to remember how to calculate the OR operation, okay? Now, the AND operation is associative, meaning you can group operands in any way and still get the same result. Let's try to check first class if they are equivalent. First, associative here for the OR. True and true, yes. True and true, yes. True and true, yes. True and true, and they are associative, yes. Now, for this one, in any way, I still get the same result. If P, Q, R are all true, the whole expression is true regardless of grouping. Let me drink water. So what will gonna happen? If P and Q and R is equivalent to P and Q, P and with calculating with the Q and R. So I will go to the store, I will go to the park, I will go to the gym. So it will be quantified as I will go to the store and the park and the gym. This result for that one, I will go to the store and the park and the gym still. That is always true. Now, what we're gonna happen here, then we'll calculate that with a truth table. So for calculating the truth table, this is how it works. We'll calculate this here, the P and Q. P and Q, remember that true and true will become true, okay? So true and true, that is true. True, false is false. False and true is false. False and false is false. So we're done with this. Calculate that with R. 3 plus the R. 3 plus true plus true is true. Then false plus false is false. False plus false is false also. And then we also have here the false and true will become false. So that is the answer. Now, afterwards, we're done with this one. And this is the results here, and we'll calculate this first here, this one right now. So for this here, let's calculate the Q or the R. For this one, let's calculate the Q and R first. So Q and R is true plus true and true will become true, and then false and false will become false, and then true and false will become false, and then false and true will become false also. So what will gonna happen? We're done with the Q and R. We'll begin to multiply that with the P. So P and true become true. True and false will become false, and false and false, that is false. False and false is false. So let's try to compare if they are equivalent. True and true is true. Yes, the equivalent. False and false equivalent. False and false equivalent. False and false equivalent. So they are equivalent associative law. So that's the process. For the distributive law, this is different. So I know this is actually a bit of interesting class, but of course this is gonna be amazing. So for the distributive law, P or tapos and, that is or over and and this is and or, so that is and over or. So the distributive law shows how or distributes over and vice versa. These laws are crucial for simplifying complex logical expression. We'll begin to calculate that in a while. So for this one here, we'll begin to prove if this is equivalent to each other. The or operation distributes over the and operation. We're trying to calculate, we're trying to distribute that actually. And this is definitely useful in terms of matrix operations in the future. If P is true, the whole expression is true regardless of Q and R's values. So say, for example, here then, what we are trying to work here is actually, if P is true, the whole expression is definitely true. Let's try to prove that later. So if P, I will go to the store. Q, I will go to the park. I will go to the gym. For R, I will go, the result will be the combination for that one, I will go to the store or the gym and the park. So the result will become I will go to the store or the park, and I will go to the store or the gym. So that is really they are still this is for this one here, and then this is for this one here, and they are equivalent still. So for distributive law, excuse me. Oh my god, it's gonna be amazing. Now it's gonna be we'll begin to calculate this first here before we'll begin to calculate. That is Q and R, so meaning we are multiplying that. So let's put the Q and R here. So Q and R, true and true, that is true. Then for F and F, that is F. Remember, calculation is multiplication. P and F is false. And F and P is false. Okay, so we will begin to calculate that with plus, okay? Because or over n. So P plus P is true. Of F and F is false. This is false, actually, right? Because this is and right here for Q and R. So of course, false times false is definitely false. Then false plus false is that P. No. It's not plus. This is the P. My bad. My goodness. So we are actually adding this P into the Q and R. That's why. So T plus T is true, then P plus F is true still. That's correct. Then F plus F is false, then F plus F is false. So F times T, yes, false, and then F times F is false. So therefore, we have to revise this. This is gonna be F times T earlier is false, then F plus F is false. So therefore, this is false. Let's try to check here then if this is gonna be, let's try to empty that, erase that and check if this will be the answer later. Okay. Now we're done with the other way around. So let's try to erase that here then because medyo ano na siya gamon. Now let's try to calculate the P and P. This is or Q plus. So we are adding P plus T. So let's try to put that here then. T plus T is true. Tapos T plus F is true. Tapos F plus T is true. Tapos F plus F is false. Now, we will begin to add that also. Here, we put that there. So P and R, T and T is true. Tapos T and F is true. R or gali. F or F is false. Tapos F times, I don't know, or T is true. So what will gonna happen? Let's try to multiply them. This is and. So we have this P and Q or Q, and we have the P or R. So true plus true times true is true. Then true times true is true. Is correct. True times false is false. And false times true is false. So therefore, this is false here. Now let's try to compare. True is equal to true, yes. True is true, yes. False and false, yes. And false, yes. So therefore, this is distributively. Now, for the and over the or, so let's try to work on this. The and operation distribute over the or operation. If P and Q are true, the whole expression is true regardless of R's value. So say for example here then, I will go to the store, I will go to the park, I will go to the gym, I will go to the store and either the park or the gym. I will go to the store and the park, or I will go to the store and the gym. They are actually the same thing. So let's try to prove it here. So P, let's calculate this first here and prove the Q plus the R. So that is plus R. True plus true, that is true. F and true, that is definitely true. True plus false is true. False plus true is true. Now, let's try to multiply that with P. True times true is true. True times true is true. False times true is false. False times true is false. Therefore, very good. Now, let's try to work on this first. P or Q. P or Q. True plus true. True. True plus false is true. False plus true is true. And then false plus false is false. Let's work on the P and R. P or R. So what will gonna happen? No. Yeah, that is and, right? That's multiplication. Oh my goodness. We're not able to oh my god. Sala siya, sala. That is and, that is not or. So let's go back. My goodness. This is gonna be amazing. So P and Q, reminder gid sa ano ha, symbol ha. P and Q, true and true will become true. True times false is false. Tapos false times true is false. Tapos false times false is false. So TFFF. So for P and R will be true times true is true. Tapos true times true is true. Tapos false times false is false. And then false times true is false. So what will gonna happen? Let's add them. So true plus true is true, and false plus true is true, and false plus false is false. False plus false is false. And therefore, check the inequality if they are equivalents. True and true, yes. True and true, yes. False and false, yes. And false and false, yes. So they are equivalent in terms of distributive property. So we're almost there. For De Morgan's laws, this is definitely like this. For not P or Q, if P, I don't know, P and Q with not, it must equates to, equals to not P or not Q. We'll see that one. Tapos, not P or Q must be equal to not P and not Q. We'll see that one. De Morgan's laws help simplify expression involving negation of conjunction or disjunction. These laws are fundamental for transforming logical expression. So what will gonna happen that here then, if the P and Q is with not, then it must be equates to not P or not Q. So the negation of a conjunction is equivalent to the disjunction of the negation. Let's try to prove that the disjunction of the negation of P and Q becomes not P or not Q. If both P and Q are false, the negation of the conjunction is true. Let's try to work on that. So say for example here then, it is raining, it is snowing. It is not both raining and snowing for in terms of this one. So for this one, it is either not raining or not snowing. So they are still equivalent to each other. Now let's try to work on with the calculation. First, so P and Q. P and Q. So let's try to calculate with P and Q. So P and Q will be here. So that is calculation. True times true, true. True and false is false. False and true is false. False and false is false. Very good. Now, calculate the not. Negate the P and Q. So how to negate that one? True will become false. False will become true. False will become true. False will become true. So this is the value for this one. So let's try to prove this one. Not P. Not P is F. Tapos not P is F. False will become true. False will become true. Tapos, ang not Q is true, will become false. Tapos, false will become true. Tapos, true will become false. Tapos, false will become true. So, what will gonna happen? False and false plus false is false. Tapos, true and false will become true. False and true will become true. True and true will become true. So, let's try to check. False and false, true and true, true and true, true and true, and that they are equivalent to each other. So therefore, this is actually the De Morgan's laws. How does that work? Now, for P or Q negation is equivalent to the not P or no. The negation of P or Q is equivalent to not P and not Q. So let's try to prove that one. The negation of disjunction is equivalent to the conjunction of the negations. Example, the negation of P or Q becomes not P and not Q. If both P and Q are false, the negation of the disjunction is true, meaning to say that if we do have here, then it is raining and it is snowing. So the result for the negation of P or Q, it is not raining or it is not snowing. So for this one, it is not raining and it is not snowing. They are still the same in actually. So for this one, let's calculate this. First, the P or Q. That is actually addition. True and true will become true. True, false is true. True or false, true is true. False, false is false. So the negation of that will become true, will become false, true will become false, true will become false, false will become true. So this is the result. Now let's try to work on this. Not P. Let's try to negate P. So let's try to put that here. P, true will become false. Tapos true will become false. Then false will become true. And false will become true. So that is for not P. Then for not Q is true will become false. Then false will become true. And then true will become false. And then false will become true. So what's gonna happen? False, that is and, that is multiplication. False times false is false. True and false is false. False and true is false. And then true and true is true. So definitely equal ba? False and false equal, false and false equal, false and false equals, and true is equals. So therefore, this is following the De Morgan's law. So for the propositional equivalence laws in terms of absorption loss, this is different. We have here the equation as P or times to P or Q will equates to P, and P and times with the set of P or Q will still be equals to P. So the absorption law simplify logical expression by eliminating redundancy when or and is combined with a part of itself. So let's try to prove if they are equivalent. If P is true, the whole expression is true regardless of Q's values. Example, P or with a set of P and Q simplifies to P. So we can actually see that later on. So say for example here then, it is raining and it is sunny. So for this one, it is raining or it is both raining and sunny. So it can be simplified to it is raining. So that is gonna our details later on. So let's try to work on with that. So P or with P and Q, let's try to work with this set. So P and Q is multiplication, true and true is true, true false is false, false true is false, and false false is false. Now, once you will begin to add that with P add with this one, true and true is definite true, true and false will be true, false and false is false, and false is false. So this is the details. For your P, true, for your P, true, false, and they are equivalent. Let's try to see. True and true, yes. True and true, yes. And false, yes. And false, yes. So this is the absorption law. In terms of the and over or, so if P is true, the whole expression is true regardless of Q's values. So with this one, with the and over or, let's try to simplify that if that will become will be equals to the true. Okay, so for this one here, then we have the proof here. It is raining and it is sunny. I mean, it is raining and it is either raining or sunny. It can be simplified. It is raining. Of course, they are still equal. Now let's try to work on that through table. So we can calculate with the P or Q. That means to say we will add true plus true is true. True false will become true. False true will become true. False and false will become false. So for calculating that with and P and this true and true is true, true and true is true, false and true is false, and false is false. So this is the result. Now let's try to copy the P. P is T and F and F. So let's try to check if they are equivalent. Two and true is correct. False. True and true is correct. False and false is correct. And false is correct. Therefore, this is actually following the absorption law. That is really so simple. Now let's work on with the negation law. Negation law is definitely P or not P will be equivalent to true. Then P and with not P will be false. Let's try to see that later. The negation law shows how negations interact with or and operation. This law simplifies expression by applying the inherent truth or negation. We'll try to see if that will be equivalent to each other. A statement for its negation is always true. Example, P and not P is always true regardless of P's values. Meaning to say for example here, then it is raining or it is not raining, the true statement will always be true. So say for example, P, you are having here that we'll compare that with true statement if that is equivalent. So P and you have the not P also. P is, the not P for that is F, then the P will become true. So if we'll begin to work on with the details for this whole one, P or not P, so or is definitely add true plus false is true, false plus true is true. So therefore, the true statement is true and true. If they are equivalent, true and true, yes. True and true is yes. Therefore, they are following the equivalence property. Now, for AND operation, multiplication of P and not P, it will returns to false. A statement and its negation is always false. Example for P and negation of not. The disjunction, conjunction of not P is always false regardless of P's values. Let's try to see that one, meaning to say it is raining, and it is not raining. It will still be false. This is always false. So let's try to see. We have the P, that true and false. So the not P will become true, will be false, false will become true. And then since this is and we are multiplying, true times false will be false, false times true will become false. So therefore, we are trying to work on with the false operation. False, checking if they are equivalent, false and false and false and false. This is actually following the negation loss, equivalence loss, equivalence property. So we also have here the implication equivalence. For implication equivalence class, we also have here that P must be equals to, we have P implications with the Q and must be equal with must be equal with their not P or the Q. Implication equivalences show how the implications if then can be rewritten using or and not. These are essential for simplifying conditional expressions, meaning to say here if this one if you will calculate this first and calculate this first, you'll begin to achieve the same that is equivalent to each other. So the implication if P then Q is equivalent to not P or Q. So P then Q is equivalent to not P or Q. If P is false, the implication is true regardless of Q's value. So we'll see that one, we'll prove that in a later. So for example, we have it is raining and I will bring an umbrella. So it will be equated to if it's raining, then I will bring an umbrella. Or for this one, either it is not raining or I will bring an umbrella. So they are actually the same and for beginning to understand that. Now, for this one here, P or Q, P then Q. Let's try to calculate that one. As what we have mentioned earlier, that the implication false lang siya if the first statement is true and the second statement is false. So true and false, that is false, and everything will be true. Okay, so that is the process. Now it must be equals with not P and Q, or Q. So not P will begin to negate the not P. Not P, we'll put that here. So true will become false, then true will become false, and false will become true, and true for this false. Now, we will be going to work on with the or, meaning to say plus false plus true will become true, false plus false will become false, true plus true will become true, true plus false is true. So therefore, let's try to check true, true, false, false, true, true, and true, true. They are actually equivalent. So that is the implication. How does that work? That is really so simple. If you know the laws of the propositional logic, you can definitely calculate the equivalence laws as well. For the contrapositive, P then Q is also equivalent to not Q, then not P. We'll begin to see that here. It is gonna be exciting. So the contrapositive of an implication is logically equivalent to the original implication. This equivalence is used to transform statement and simplify proof. Let's try to see here. The contrapositive of an implication is the negation of the conclusion implied the negation of the hypothesis. P then Q is equivalent to not Q, then not P. If P is false and Q is true, the contrapositive is true. So therefore here then P then Q, not Q is equivalent to then not P. It is raining, I will bring an umbrella. For this one, if it is raining, then I will bring an umbrella. And for this one, the result, if I will not bring an umbrella, then it is not raining. So of course, they are equivalent to each other. So for this one here then, P then Q. So as what we have mentioned, P then Q is will return false if the P is true, then the Q is false. So true and false, that is gonna be false, and the rest will become true. Okay, take note. Now, not Q. So we'll begin to negate the Q. So put here, Q is true, it become false, then Q will become false, that is true will become false, and false will become true. Then we have the negation of P, will also negate P. So true, we have, no, P we have will become false, and then P will become false, and then false will become true, and then what happened? False will become true. Okay. So Q ang una. So this is not Q. This one here. And this is not P. So, then this one, first statement, if si Q, if it is true, then ang P mo, if is false, therefore ma-false siya. Ngitaon ta. So, true for not Q, then this is true, actually, this one, true. And then this is false, so therefore this will gonna be false. So the rest, false, false is true. False, true is true. True is true. So therefore, let's try to check if that is equivalent. True is true. False is true. True is true. True is true. They are equivalent to each other. So that is actually the end of our loss. I know that is actually overwhelming, but of course that is really so simple. So the constructing truth table for equivalences, truth tables are their purpose show the relationship between the components of a logical expression and its overall with truth value. They are used to verify the equivalence between logical expression. How to create a truth table step by step? Start by listing the possible truth values combination, component proposition, and apply the logical connective step by step to determine the overall truth value. If you really know the rules or laws class, you will definitely understand that the process actually. This is really so simple. Prove equivalence for P or not P. Construct a truth table for P, not or not P to show it is tautology. Prove equivalence for P or Q, and Q, then or not R. Show how the truth table for P or Q, and Q, or not R. Proves its equivalence. We'll begin to see that actually. This is gonna be exciting if we'll begin to calculate this one. It will be a good thing if we'll begin if in the exam you can actually do this as an exercise as well. If you wanted to calculate this first, here then you can do so. Okay. Now, practical applications for the propositional equivalence. So, in computer science, propositional logic plays a key role in designing algorithm data structures and logic gate using Boolean algebra to simplify logic and programming. That's why I have mentioned to you that if this true or false propositional logic is definitely useful in a lot of courses, as we can definitely get the optimized value through statements or whatsoever. And for the mathematical proof also, we can also apply the logical equivalences there, simplify complex proof by reducing expression to simpler forms, making a reasoning proof construction more efficient because we can try to track class if that is equivalent to the certain goal that you are trying to work on. For digital circuit naman, propositional equivalences are used in optimizing logic circuit, ensuring fewer gates are required and improving performance in digital systems. So in our logic gates later on in our midterm term, we can definitely work on with that one, how to run through with the process, and that is really gonna be amazing. So the everyday decision making logic is often used in decision making processes where people analyze possible scenarios and make reasons or conclusion based on logical arguments. So of course this is gonna be good since this is in everyday life. If we begin to work on with true false, you can quantify if this is based on your decision, if it is what will be the relationship based on the connectives, for example, you can quantify that. For propositional equivalences, this is actually essential in logical reasoning because they simplify expression, making logical proofs and evaluations more manageable. Understanding tautologies, contradictions, and equivalence laws is crucial for working with complex logical statements and drawing valid conclusions. So for this one here, then you can calculate many things actually, class, because of course, um, by defining the true and by defining false with a particular connective, you can actually map out what will be the direction. And of course, if you're trying to check the equivalences, what will be your goal if they are equivalent to each other? Of course, it is boom, it is definitely equal to each other. And of course, you're the one that you were able to the plans that you are trying to plan out in the first place, if it is after calculating that one, if this is correct, so of course your project will be definitely be good. So in your GUI, actually, this is your I know that you're trying to use with propositional logic, since propositional logic is definitely useful in such cases to solve such complex scenarios. Of course, I know that you can prove that one, and I'm also trusting to you. And of course, guys, in this particular video, you have to put 5 sentences in the video explanation as your plus points, and make sure to your takeaways of this video. Thank you so much, and have a great day and good luck with your examination. In the next video, I'll be going to provide the calculation, get step by step for the truth table, so that you will also learn and how to work on that. Thank you so much and goodbye.